I'm going to do this in two parts. The first part of assessment is I'm going to think about the limit. So I'm going to eliminate having to worry about basis set. I'm going to talk a little bit about the limit for geometry and a little bit about the limit for energy. And I'm going to look at just a couple of different methods. I'm going to look at, I'm probably not even going to look at Hartree-Fock theory. I'm going to look at some of the functionals, and I'll touch on it in P2 a little bit. And then after talking about the limit, I'm going to talk about how large a basis set does it take to reach the limit. Now, you can't do complete basis set calculations. People talk about it, but you really can't do it. What you can do is pick something that's large enough that, again, adding more things or cost really doesn't do anything. I'm going to be using, I'm not going to be saying it, but I'm going to be using either this one, these are Aldrich basis sets, either this one or that one. These are significantly more costly than the ones I want to use in practical senses, and this one called augmented is extraordinarily costly. But you can do things that are small molecules. Okay, equilibrium checks. If I really am interested in really tiny molecules, the experimental data comes from the gas phase, things like microwave spectroscopy. You can actually measure things to a few thousandths of an angstrom in a bond weight. That's the thing of interest. You can actually get extraordinarily accurate. So we have in really tiny molecules the ability to say how good can we do. And if I look at that, I'm going to look at a set. I'm not telling you what the set is. It's about 50 molecules, small molecules which have microwave structures. I'm just looking at carbon, oxygen, carbon, nitrogen, distances, things like that, simple. You can see here that the experiment can get to about 0.005. Below that, it's meaningless. You can see that theories are actually getting pretty good, and V3 lip is extremely good. You're actually very close. All the theories are quite good. If anything, Hartree-Fock theory is a little bit worse than the other ones. This one is turning out to be a little worse, which is unfortunate. But you can see they're all pretty good. So this is looking at the mean error of my collection of 50, 60 molecules. Now, in reality, there are two things that I should comment. One, you really can't do calculations on large molecules with that theory. You can, but it's really very, very costly. The second reality is that with the exception of a few hundred very small molecules, all of what we know about structure comes from X-ray crystallography. There, the error limits are much larger. They're something like 2/100ths of an angstrom. That's if you're lucky. And so what it's really saying is not that I can't calculate better, but I can't really know that anything below about 2/100ths of an angstrom is actually closer to experiment or not, because the experimental precision is likely to be that. So I think we have to change our standard in saying, can we get within about 2/100ths of an angstrom? If we can, then we're fine. Here's the same set. I've put them as plots now. And what you'll see, this is one functional. This is XD, which is the one I personally like. And what this is doing is it's comparing small molecules with two different basis sets. The first basis set is this, compared to my limit. The limit is here. It's the same in both plots. And you can see this is essentially perfect. And the second one is really getting small, and it's pretty close to perfect too. What this is saying is that geometry is easy. If everything were this easy, one could go much further than one can right now. But geometry is easy. What it's also saying is don't spend a lot of time using very good methods to get structure. How easy? Let's replace the geometry by, let's just look at these two in a second. Let's look at that. This is the same set of molecules as I showed you before, the same axis. And now let's use a geometry which is really simple. Hartree-Fock with a really tiny base set, 321G. Okay, about as simple as you can get. And you can see now that you're falling off the line. Here you were pretty close to the line. Here you're falling off. So you probably have to be a little bit cautious on going below this 631 star. But again, geometry is easy, and you're clearly getting the trends right. Let's now look at thermochemistry. Experimental thermochemistry is something that is conceptually very easy, but in fact is not commonly done. It's a destructive experiment. You have to burn things, and the quantities are actually fairly large. In practice, the experimental thermochemical literature is pretty small, a couple of thousand compounds. And if you look at errors, there may be plus or minus 8 kilojoules, about 2 kilocalories for hydrocarbons and oxygen compounds, oxycarbons, where the combustion products are well defined, carbon dioxide and water. And if you go to other elements, even simple as nitrogen, the errors are quite large. There's a very strong reason to not use experiments to judge practical theories, because the errors are really quite large. They're well known for some small molecules, but as soon as you get to things that are more than a few atoms, experimental thermochemistry is not very good. What we're going to do is we're going to use mainly coupled cluster theory, which is also small molecules, but much more consistent. And then as I start talking about things that are larger, I'm going to use G3MP2, which is an approximation to that. The first one that people always talk about are reactions of break bonds. This is not a very important reaction. However, if you can describe the energy of bond breaking, you probably can describe the energy of a molecule combining with another molecule, in other words, an activation energy. So bond breaking is an extreme example of essentially a reaction energy or an activation energy. So it's an example that's worth using. Okay, if you do this, these are limits now. The first thing I want to do is I want to mention the most commonly used correlated model prior to density functional theory, MP2. If you look at MP2 on bond dissociation energy, it's terrible. This is well known. People still do it. And if you look, this is, 20, 30 molecules, simple, and I'm using the calibration here is G3 because some of them are quite large. And you can see here that there's clearly a systematic error. The G3 number is too large, but there are also random errors that are getting huge. They're getting to be 100 kilojoules. So MP2 is really not a very suitable method for doing bond dissociation or for doing activation energies. I bring this out because this is probably the most commonly used method for that purpose. If you look at density functional theories, you see some scatter, but you're now clearly significantly better. The systematic error is sort of disappeared. Here in MP2, you clearly had a systematic error. Here it's less so. This is the XV function now. The mean error here is probably something like 30 or 40 kilojoules. Here it's 10. If you look at different density functional theories, this slide, what you'll see is the modern ones are all sort of similar. The one I showed, they're all 9 or 10. B3 lit is not as good. And what this is to be expected because you've now parameterized the modern functionals. Every one of these have now been parameterized to match thermochemical data. So you'd expect they would better match in theory it's not. But you can see there's a serious factor 2 in quality. Probably the most important kind of reaction are reactions that conserve the number of electron pairs. This is something where I compare isomers, for example. I've given just a few simple examples here. Acetone has several isomers here, a few of them are listed. So if I want to write a reaction where I'm comparing energy that and that, if you look at this, the number of electrons is the same, the number of electron pairs is the same, but where I'm differing is I'm changing the numbers of different kinds of bonds. This one has one CO double bond, none of the other ones do. This has a CO single bond, this one has a CO single bond, these do. But also it's a CC double, these two have much in common. These three have much in common, but they're different than these. So these are rather common kinds of reactions. I'm going to show this to you in a funny kind of plot. I'm going to give you, the red line is, this is for a set of, I don't know, roughly 20 examples here. This is for a set of isomer comparisons among simple molecules. The red line is the experimental line. The green dots are G3. This again is an approximation to a theory that we think is equal or better to experiment. You can see that there is a pretty good correlation between the line and the green dots, although there are distortions, there are deviations. Deviations are probably the experiment. The black bars range of density functions. If you have a little tiny black bar, let's pick one outside, this says that the density functional theories are all very similar to the reference, and they're all very similar to each other. Here you have, pick one I can see, I have a wide range, and they go from being off by one sign by being off to another sign. The experiment and reference G3 are in the middle. So I want to make a couple of points here. One is that density functional theories are not perfect. They're not always getting close to actually what we think is the correct answer, either experimentally or from a reference calculation. The second point I want to make is the density functional theories are showing a great deal of variation. And so it is necessary not only to use the word density functional, but actually define the functional you're using and judge how good it actually is. Here is a set of larger molecules. Actually, this is from a subset that I use. These are all the reactants products of vein organic reactions. I have about 40 of them that I use. And if you make the same kind of plot here, before the plot, let me put deviations. This is looking at isomerization energies, and I put here, this is a subset of the ones I'm actually using. And you can see here the deviations vary from Hartree-Fock theory, where the mean is huge, the maximum is enormous, to B3LYP, where the mean is actually quite large, the maximum is quite large. The remaining density functional theories, and you're seeing some variation here. You're now seeing in this particular set I have a feeling this is actually a mistake on my part. This should not be that bad. But you're seeing here, generally, they're better, the modern theories are generally better than B3-LYP, the one that's used, but they do differ. Here I'm showing you the difference in graphical form. This is the best of those theories, which is, pick that one, versus the worst of the density functionality, which is that one. Here, what it means to be bad, you can clearly see that plot agreement is much less than that plot agreement, where the reference is G3. The last class of reactions are reactions where you actually maintain numbers of bonds. This had an old word coined in the 1970s called isodesic. Iso meaning equal and desmus meaning bond. And they encompass a large number of reactions. They encompass all stereochemistry. They encompass things like cis-trans isomerization. So if we maintain bonds, we change the environment. The standard example I use is this, where I'm looking at the proton affinity of some molecule, trimethylamine in this case, versus a reference, ammonia. If you look at this, the bonds are actually maintained. I've moved them around, but if you count number of CH bonds, NH bonds, it's exactly the same. If you look at that, you get a very interesting result. I'm going to bring in Hartree-Fock theory. This is really much simpler than any of the density functional theories. And even Hartree-Fock theory, over a very wide experimental range, is extremely good. If you bring in best of the density functional theories, or one of the good ones, at a very large basis set, these are both very large. It's better, but they're both extremely good. So the point that I want to make is that the choice of reaction, writing things that balance, is much better described than were you to write something that doesn't balance. Now, these limiting basis sets, I've been using this one, are probably too large to be used routinely. There are two ways to reduce faults. One of which I've actually been doing without telling you is to use this base set only for energy and to get the underlying geometry with something similar. All the results I've actually shown you have been using these much simpler geometries. There's a nomenclature for this. The nomenclature for functional is method/basis set. I'm using that method with that basis set. If I want to use a different method for energy and geometry, the nomenclature is to the left, method basis set. I'm doing this for energy. / terrible nomenclature, method basis set for geometry. So what I've been doing is this, and then without telling you, I've been doing that for geometry. Can you get away with what I've been doing is this geometry? Can you get away with things that are even simpler? And so I'll look back at my set of reactions. Again, this is just the first few, and ask the question: can I use even simpler geometry, Hartree-Fock structure, to get energy? And here I'm going to do a plot. This is exact, good geometry. Here is much less costly using that. And if you look at that, it's very good with one exception. And the exception is actually this reaction. And it turns out that simple geometry on the amine oxide is extremely poor. So you have one molecule which falls off the line. The rest of it is a positive experiment. The other place to save cost is to try to replace your good energy using that. They said, can I make that smaller? And here I'm going to give, this is the same set of reactions. So it's typical isomerization where bond counts are changing. So, I'm balancing numbers of bonds, but numbers of individual times are changing. If I try to use, instead of the Dunning base set, I use something that is significantly less costly, factor of 10. It's essentially perfect. Here I'm using something that is probably 100 times less costly, 61 star. It's not as good.